You should grow, right? Yeah. Dear Heavenly Father, we thank you for this day. I thank you for the students. Just pray you with us today. Help us to glorify you, Lord, in what we do. In your name I pray, Lord Jesus. Amen. So we have a visitor today. So what I was talking about, what we have been talking about up until their first, up until we changed past the first test stuff, but the whole first part of this course is on, so you know the quadratic equation, right? No? No? So quadratic equation is this thing, ax squared plus bx plus c equals to 0, right? No? You don't know how to, when we solve this, we get solutions, if they exist, are minus b plus or minus square root of b squared minus 4ac over 2a. No? Oh. Phooey. Well, you're not there yet, but you'll get to this in high school, I'm pretty sure, but you better get to this in high school. Anyway, so the first part of this course is basically investigating, is it possible to generalize this for higher order equations? And it turns out you can do a similar thing for third order, and you can do a similar thing for fourth order. The third order solution formula is like a half a page. The fourth order thing, if you really were to write it out in complete detail, it'd be like a whole page. It gets quite awful. No one actually wrote the formulas in here, but we understand how to put them together piece by piece. But then something funny happens. At order 5, there ceases being a formula like this. And from that actually stems the birth of what we call group theory, which is one of the major stories in mathematics over the past 200 years. But of course, you probably wouldn't see it unless you were a math major, right? But actually, those same groups are used in physics to describe symmetries of particles that we see, like radioactive decay is in terms of group theory. Nuclear physics is in terms of group theory. Group theory is an important thing to understand the way our world works as we currently understand it. But anyway, I have to get back on track in here. So I just wanted to give you something that you could say you learned something in this silly class. Because everything else I'm about to say will be completely ridiculous. Although much of what I say is ridiculous, but that's just because I am who I am. So we have talked about the co-kernel, right? I was interviewed for a job at Coker College. You guys know about Coker? Yeah, it's a college, and although I think it may not be spelled C-O, is it spelled C-O-K-E-R? Huh. Disappointed I didn't make more Coker jokes there. Just be like, there's still time. No, I was in my interview, and I talked about doing undergraduate research, and one of the faculty actually laughed in my talk, like I suggested that some undergraduates in principle could investigate certain questions of supermath, because they're questions which basically are souped up calculus, And she laughed out loud during my talk. I'm like, not cool. Not a friendly laugh either, like a, that's ridiculous. You don't know who I'm teaching here kind of laugh. Sadness. Anyway, I guess at that point I should have just been like, all right, see ya, everybody. Skip my talk with the dean and the rest of them, just like, all right, I'm out. Oh well, anyway. So we introduced the co-kernel. We said that the co-kernel 0 means that the map is surjective. Past that, we can talk about the first, second, and third isomorphism theorems, just like we did in linear. They look essentially the same, and even the correspondence theorem looks the same. So I wanted to push past that. Next, he talks about, so I'm just going to do some reading here, and then I'll start writing again. He defines a left R module as being cyclic, if and only if it is the quotient, if it's isomorphic to the ring underlying the module, quotient some left ideal. So this is definition of cyclic. And then he defines a simple R module. What is it? M is a simple R module if M is not equal to 0 and M has no proper non-zero submodules. So simple. What was a simple group for us in last semester? It was one of the least simple things in the course.
The only ideals were 1 in the whole group.
The only ideals were 1 in the whole group, right? So essentially, it doesn't permit any interesting quotients. Right? There's no factor group except for the trivial factor group or the whole thing, right? Either you divide by the identity and you're right back where you started, except with an annoying notation where points have been replaced by singletons. But then you throw away the set, so back to isomorphism, you're back to the group, or you mod by the whole group and you're just left with the identity. So that was a simple group. So a simple R module is likewise one that doesn't have it doesn't have any interesting, in some sense, submodules. We can form the quotient module because, remember, we have the structure of an additive group, right? So normality of the subgroup as an additive subgroup is not in question. So the factor, the factor module is something we can build. Just like you may recall from linear, we could define quotient vector space for any vector space, right? In contrast, when we were in group theory, we needed a condition to form the factor group, right? We needed that the subgroup was normal. Because you could have the situation that the left and right cosets were not equal, and left and right cosets not being equal would mean that you can't define the operation on the group like you'd like. So for example, is example 6.24, an abelian group is simple if and only if it's isomorphic to, well, he calls it IP. What is IP? That is the cyclic group of order P. Yeah. It's the pth integers. It's like integers, but mod B. Yeah, that's his notation. So that was vexing to me when I first saw it until I was like, oh, that's kind of a reasonable notation because you get into trouble with the p-adic peoples. P-adic peoples mean something different by this. Something very different. So anyway. All right, next he talks about internal versus external direct sums, and the story there mirrors vector spaces again, so I won't say much more about it. His proposition 6.26, he introduces injections and projections that sort of describe the external versus internal direct product in terms of maps. All right. He defines the internal direct sum. What does it mean for M to be the internal direct sum? What do we mean if we say a module is the internal direct sum of S and T? What's that mean? I think that's true, but that wouldn't be my definition. I mean, I would say this means that. Also true. I'm not sure. That's a good question. Like, that actually corollary 6.27 does give that is one of the part 3 of corollary 6.27 says that's one of the equivalent conditions for reproducing the module as an internal direct sum is that each element in M has unique decomposition into S plus T, where S is from S and T is from T. Yes. Yes. So this would mean that there exists a isomorphism to S cross T, where that's the Cartesian product of the submodules S and T with respect to the usual, we add component-wise, we scalar multiply component-wise. All right. So that's what it means. The internal direct sum means it's isomorphic to the external direct sum. And then he says, and by the way, we'll start writing that this is also equal to S plus T. And you'll just have to know from context whether we're actually talking about this or this. So anyway. When people are conflating these two things, they'll write things like this, right? X plus Y is X comma Y. I mean, that's the kind of thing. If you see an equation like that, you should realize that they have identified the internal and the external direct product in the discussion, right? Where's a place we do that? About complex numbers? I don't know. We shall see. Let's see here. Let's see here. Then this is a new definition, so I should write this down. Two definitions, actually. Definition S submodule of left module M, then is a direct summand of M if there exists submodule T such that what? Can you fill in the blank? Right. Yeah. So that means there exists a complementary submodule, basically, right? It's a direct summand. S is a direct summand if there's some complementary submodule which forms the direct sum.
So that doesn't always happen?
No. A submodule, S is a submodule of a left module M. S is a retract of M if there exists an R module homomorphism, rho from M to S, called a retraction. All right. What does it mean for it to be a retraction? That means that rho of S is equal to S for all S and S. All right. What's the connection between these ideas? The following corollary tells us that. Corollary 6.28 says a submodule S of a left module Rm is a direct summand if and only if there exists a retraction. Well, that's kind of an interesting idea, right? We're trading a statement about sets for a statement about maps, right? I mean, the existence of a retraction is, well, that's a statement about homomorphism. It's about functions, whereas this direct summand is a statement about, the existence of a subset, a submodule, right? So apparently, we can work in either world. Yeah. Let's see here. So let's at least do part of the proof of this. It's a corollary to what? Oh, it's a corollary to the proposition 6 point. I'm not sure what this is a corollary to. We'll find out in a second here. It's a corollary to the definition. Well, I don't know. He says let. I'm just going to write down some formulas here, see if we can make sense of them. I think this may be, I probably should bail on this right now, because I think it assumes heavily the thing I haven't written down and just glossed over. Yeah. So in this case, we let I, going from S to M, be the inclusion. So what's he assuming at the start? I think we're going, at the moment, I think think we're working on this part of the proof, right? We're supposing that it's a direct summand. And he says, let I be the inclusion. Wait a minute. We show that M is S plus T, so I'm wrong. All right. I don't know what it is. He's just... I guess we could look at the inclusion of a submodule, whatever else we've assumed, right? I mean, that's independent of the assumption of direct summand or retraction.
It's the identity map with extended.
Right, so that I of S is equal to S, right? For all S and S.
What does he mean by in the case?
Oh, yeah, what does he mean by in the case? Dang it. You got me there. In this case.
In the case that
He says we show that M, well, he says we show that M is equal to the direct sum of S and T, so maybe he's working on the converse direction. Let's just go on and read more. Where T is equal to the kernel of rho. Okay, so he is assuming this direction, guys. So he's assume that there exists retraction. Right. And then he says use I to denote the inclusion of the submodule in M. All right, that's fine. Then what's his next move here? He says if M is an M, then we need to add 0. M is equal to what? What we've got to work with here is what? Rho, right? So basically we want to add and subtract copies of the retraction of M. So we do something like, let's see here, what's his notation? M minus rho M plus rho M. Right, where he's just omitting parentheses. That's a map acting on an element, right? But we just abbreviated notation, don't write the parentheses of. Now, where is rho M? Right. By construction. And how about the M minus rho M? What can we say about that? What happens if we look at this? If we look at rho of M minus rho M, what do we get?
and rho of rho m is just rho m.
Right, because rho M is an S, and the retraction fixes elements of S, right? So this is rho M minus rho M, which is 0. Therefore, M minus rho M is in the kernel of rho, right? And what's that tell us? He says, thus, M is S plus T. Where he's defining T to be the kernel of rho, right? So to show it's a direct summand, we need one more thing. Yeah, we either need uniqueness or we need to show the intersection of these two things is 0. Or, well, I'm not sure that actually is that. Yeah, that's part 2 of corollary 6.27 says that the unique representation is still equivalent to the intersection of the two submodules being 0. So we still have that. So what happens if you assume that M is in S and T?
It has to be 0 because rho maps everything in S to itself. So the only thing it can map in S to 0 is 0.
And then what'd you say? Oh, but and rho of m equals to m is what you're saying. Yeah, okay. So anyway, so the intersection is 0, and we've proved then that m is the direct sum of s and t. Yeah.
Wait, where did we use I?
We didn't. That's true. I think I gets used. I hope I gets used in the other direction, maybe. For the converse, if m is the direct sum, then each m has a unique expression of the form m is equal to s plus t, where s is an s and t is an t, and it's easy to check that rho from s to m is defined by that as retraction. I don't think he used I. This is very uncharacteristic of Rotman. Huh. Man, I am not seeing it. I think that could be deleted. Huh. Shame on you, editor. Let's see here. Sorry. Wait a minute. Who's the editor? Should be careful. He's going to watch this. All right, anyway. And then he extends external and internal direct sums to multiple submodules rather than just two. All right. And by induction. Anyway, it's more complicated, of course. The independent submodule condition is that you have to have the ith submodule intersected with the direct sum of everything except for the ith one is 0. Independence of submodules, just like independence of subspaces, is a little bit delicate. And then he has a proposition, but again, the equivalence of the unique representation and the independent submodules is given. All right, so it's still, we have that either, you can write each element in the direct, each element in M as a direct, as a sum of elements of each of the submodules in a unique way, or that's equivalent to saying that the intersection of the ith submodule is 0 with the direct sum of everything except for the ith submodule. In other words, unique representation is still equivalent to independent submodules. And then his proposition 6.31, where he looks at the quotient of M1 that cross Mn with S1 Cartesian product of the Sn, where S1 is a submodule of M1 and Sn is a submodule of Mn, and likewise all the way in between. And when you look at the quotient of the product with the product, you get the product of the quotients. So it's like, so basically this. Oops. Oh, all of a sudden I picked up a second one. Sorry, I don't know how that happened. And of course not equal, but isomorphic too, because those are different objects, but yeah. Yeah. All right, and then finally, we get to what I had advertised for today, which is sequences. All right, so let's get into that. So definition. A sequence of R maps and left R modules, right? So here's where it looks like, here's the diagram for it, dot, dot, dot. M, n plus 1, Fn plus 1, M, n, Fn, M, n minus 1, dot, 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 all right, is called an exact sequence if the image of the n plus 1th map is equal to the kernel of the nth map for all n. Well, there also exist sequences with the opposite numbering. But this is the numbering which ends up being interesting to a lot of applications of this. But I think the answer to your question will soon be somewhat forcefully given by the theorems I'm about to write down.
So is this just saying the composition of any two adjacent functions to the theorem?
Well,
Or is it saying a little bit more than that, right?
I think what it's saying should become clear as we go on here, but I wouldn't attempt to say that just yet. But hold that thought. Hold that question. There's a little bit more. So we just write 0 instead of 0 in these diagrams, and also, the same. So we just write 0 to a, right? In fact, what he says is really, there's no need to label this f, and there's no need to label this g. There's really no need to label the maps going to 0 or coming from 0 there, because such maps are unique, right? Because either f has to be the 0 map or g has to be the 0 map if it's an R map.
Well, even if, regardless of what kind of map it is.
Yeah, that's fair enough. It's not even an R map thing. It's just a set theory thing, right? So this is something we should be teaching in Math 200. Yes. Back before my brother was tamed by students, he used to talk about putting universal principles into Math 200, essentially. Like a couple weeks on category theory and natural principles, introducing students to, well, real mathematics. I haven't heard him say that in a few years. Let's see here. Teaching has cured him of that. Let's see here. At some point, you stop caring about optimal production and you start caring about mass production. Let's see here. It's unfortunate, but true. All right, proposition 6.32, and this may answer your question in part, Sam. A sequence 0, A, B, 2, a sequence B, A, 0. I'll add some more letters here. A sequence zero, A, B, 0. All right, let me add the punchline and a little bit more decoration here. Is exact if and only if, here's F, if and only if F is fill in the blank. All right. And here, I'll put the G between going from B to A is exact if and only if G is fill in the blank. This is exact if and only if H is fill in the blank. So you said surjective? Ah, stink. Trying to trick you. Didn't work. Yeah, injective, surjective, and indeed bijective. let's just talk through it a little bit, right? So if we assume that the sequence is exact, right? Then what does that tell us about f? What's the the kernel of f is equal to what?
The image of a set with one element can only be one element. Zero.
It's the image of the zero set, right? So the image of this map, right? I mean, the only mapping here is the zero map, is the point. Yeah. And you write 0 since 0. So anyway, so that says that this is 0, so therefore f1 to 1. How about the other direction? What do we need to prove that that sequence is exact?
Well, f being objective is equivalent to the kernel being 0. So we get both directions.
So we get that the kernel of f is equal to is equal to 0 by assumption, right? Therefore, kernel f is equal to the image of, let me give this stupid, we need to, I mean, really to prove this worth anything, we should give this a name like f tilde or something stupid, right? Yeah. And so that's all there is to check, right? And then, yeah, right. I'm trying to, I find when we're starting, it's helpful to not biconditional as much, but yeah. You could disagree, and I would respect that. So 2, let's see here. That sequence, I'll try your biconditional here. So sequence being exact is if and only if what? Let me call this thing G tilde. The kernel of G tilde is A by the given diagram, yeah. So this is if and only if what? But yeah, your heart was in the right place. And then finally, part 3 follows immediately from parts 1 and 2, right? Because you can apply basically part 1 on the left and part 2 on the right, so you get H is both surjective and injective, which is to say H is bijective. Okay? So next up in this cavalcade of weird ideas, we have what's called a short exact sequence. So the name of the game here, guys, is to come up with sequences with particular properties which encode data we're interested in about sets, right? So like one of the things which is upcoming is that there are short exact sequences which are essentially equivalent. The existence of the short exact sequence is the same as saying there's a second isomorphism theorem or there's a third isomorphism theorem. It's a really interesting way of repackaging ideas that we already have in terms of sequences. So anyway, here we go. A short exact sequence is an exact sequence of the form 0, A, B, C, 0, where we'll use F and G for the middle maps. And he says we also call this a what? We call this short exact sequence, which I'm going to abbreviate as SES, an extension of A by C. And then he says we also sometimes call the middle module B an extension of A, right? Okay, so before I even write the next thing, which I mentioned, what would that say about the kernel and the image of the named maps there? I think that says 0 is equal to the kernel of F, right? And what else? Fair enough. Wait a minute, how did you get that? Oh, you're using the proposition? Okay. Let's see here, I'm not sure it's more interesting, but we also know that the image of F is the kernel of G, right? All right, well, anyway. And I mean, if I can, again, do some stupid labeling, if this is F tilde and this is G tilde, to say that's exact means that the image of F tilde is what? Kernel of F, right? And the image of G is the kernel of G tilde. And of course, if we get into the details there, we're going to get back into what we were just doing. But trying to drive in the definition of exact sequence for you guys. All right, proposition then. 6.33 says 1, if we have 0, A, B, C, 0, a short exact sequence, all right, then, actually I'm going to write over here, then A is isomorphic to the image of F, and B, mod the image, is isomorphic to C. Two, if T is a subset of T is a submodule of S, which is itself a submodule of M, tower of submodules. Right. Then there exists a short exact sequence, and that short exact sequence is 0 goes to the quotient of S by T, which goes to the quotient of M by T, which maps to the quotient of M by S, this being F, this being G, that goes to 0. And he says that these are the second and third isomorphism theorems, which of course you guys have memorized from your previous coursework, but kidding. Let's see here. Does this first one make sense to you guys? A is isomorphic to the image of F. How would we get that? Whoa. That's kind of surprising.
Is it just saying that F is an isomorphism?
Yeah, well, it's an isomorphism to its image. Because it's
Oh,
any injective homomorphism is an isomorphism.
So you guys are, okay, so what you're thinking about is using the first isomorphism theorem on this right here, right?
well, we're just saying that we already know that F is injective,
Right.
and then,
Well, my point is that A mod the kernel, right,
Yeah.
of F is isomorphic to the image of F, right?
Yeah, you can do that. But you can also just say an isomorphism is something that's injective, surjective, and homomorphism. Where you
Oh.
can is injective, and then surjective to its image, obviously, and then homomorphism we're given.
So you say it's just clear that F is a bijection by that diagram.
Bijection to its
Bijection to its image, right?
right.
Oh, okay. So I got you. So we already know that F is injective when we write that diagram. Where's that come from? Because it goes back to part 1 of proposition 6.32, right? Okay. Cool. So this is overkill.
Yeah.
Sprano. All right, and then the quotient by the image. How's that? Is that the first isomorphism theorem? What's that?
Yeah, I think so.
So there we.
The kernel of G is equal to the image of F, and then G is surjective. So yeah, that's the first isomorphism.
G is surjective. On 2's easier to write. So G is going from B. I see. Yeah. So that is first isomorphism theorem. And then for part 2, he uses what's called enlargement of coset. So for part 2, basically study the map. Well, he says, you can draw this diagram. Then the question is to define these maps. So he says F from is just inclusion, which makes sense because S is a submodule of M, so we can just do F of x plus t equals to x plus t. That makes sense, right? Right. But then the G is a little bit more exciting. The G, we do G of x plus t, by definition, is x plus s. This is the so-called enlargement of coset map. And then he says, as in the proof of theorem 6.21, G is surjective. The kernel of G is S mod T, which is the image of F. So, yeah. And then finally, one last definition and theorem, and we'll be done for today. In fact, we'll be done with this section. I would encourage you to read the rest of it. I need to move on.
Is this just the rest of the stuff in the PDF?
Yeah, in the PDF. We're near the end at the moment. Definition, a short exact sequence. So 0, A, B, C, 0. And he's going to I for the map between A and B, and P for the map between B and C is split. All right? If there exists a map J going from C to B, all right, with P composed with J, being the identity on C. All right, and here's why that's interesting. If, if the exact sequence above, if the exact sequence above is split, all right, then B is isomorphic to the direct sum of A with C. And I think the proof is pretty. I think if you read the proof, you'll understand it. I don't have time to go through it at the moment, but so that's why a split.
Does this use the corollary 6.28 about retraction?
I don't see it in my read right now. That's what I was kind of expecting, Sam, but I don't see the retraction corollary coming up here directly. But maybe it's used in a step that I don't understand just looking at it here. Then he warns us in example 6.35 that the converse of this proposition is not true. There exist exact sequences, all right? There exist exact sequences with three things with bookends of 0, where B is the direct sum of A and C, and yet is isomorphic to the direct sum of A and C, and yet the sequence is not split. So this is not an if and only if. This is an if then, right? And he gives an explicit example. He then defines left and right noetherian, all right, which we'll hopefully talk about in a future. I mean, what does it mean for a module to be noetherian? That's a finite condition, finiteness condition. When can you finitely generate a module? It's said to be noetherian, in honor of Emmy Noether. Yes, when it is true, when Noether comes in, it does get interesting. And then finally, his last proposition concerns faithful are modules and finitely generated, and a specific comment about complex numbers. But anyway, I'm going to probably, well, I don't know, I'm still debating whether or not I should scan another section of this book, because I do love this book. But on the other hand, Dumb and Foot doesn't require me scanning, so I'm lazy and probably go back to Dumb and Foot pretty soon. But I think next, it's likely I'll do tensor products of modules next, but I should think about it some more. That's also just me being lazier, because I kind of remember how tensor products of modules go. Some of the other topics would actually require time on my part, which I don't have at the moment. So, yeah, sorry, I will not be around Monday, by the way, guys. Okay.
Yeah.